All right, here's our first video of the semester. And it's mainly just problems. I know you're going to be worried about your little practice quiz, so let's do that first. So I've given you a vector v and a vector w that are given to be 3D. You just don't have coordinates for them, so they stand for any 3D vectors. Your answers are going to be v, s, or n. So let's take a look at this one. V cross w. Well, since v and w are 3D, this is defined, and it will be another 3D vector. It'll be a vector perpendicular to both of these two vectors, but that doesn't matter. It's a 3D vector. That's what we want to know. And a 3D vector dotted with a 3D vector is going to be a scalar. Now, we could say more in this case. The vector v cross w is perpendicular to both. It's perpendicular to both v and w. So not only will this be a scalar, it will be 0 because this is a vector that's perpendicular to v and it's dotted with v. And if you remember, the dot product detects perpendicular vectors by giving 0 because it's got cosine in the formula, and the cosine in 90 is 0. So this not only is it scalar, and that's all you have to answer for the quiz, but you can see or think about it that this answer is actually going to be 0 and not 0 vector, just a 0 scalar. You could sort of imagine it by thinking of v and w forming some kind of corner, and then the cross product of v and w is the third vector at a corner, and that vector is being dotted with v, so that's still a corner. So, dotting with a dot of perpendicular vectors is going to be 0. Number 2, do in the parentheses first. So you've got w dot v, that's defined. That's a 3D vector dotted with a 3D vector. That's going to give you a scalar. And now you got a scalar crossed with a 3D vector. Well, that's no good. You can only use the cross product with 3D vectors. So that's a nonsense answer. And now I'm mentioning something that's in the book. If you read the book, they refer to this as the vector triple product. And you have a vector crossed with a vector dotted with a vector. And as we just saw, if you put parentheses around the cross product, the answer is a scalar. If you put parentheses around the dot product, the answer is nonsense. So the math people of the world decided, well, look, who would write it as nonsense? It must mean do the cross product first. And if you do the cross product first, you get a scalar. And this scalar happens to be really interesting. This scalar is the volume of the box formed by the 3 vectors. So if you use your hand, with the 3 vectors like that, you can imagine the 3 vectors forming a corner of a box and just fill in all the sides parallel. So you get, what a box looks like. You get this little box. And this compilation here stands for the volume of that box. Now, it might come out to be negative, but that just means, take the absolute value of it, of your answer. It also means that the 3 vectors, the order doesn't matter because the 3 vectors form the same box. So this is really actually quite a remarkable thing. The book goes into a couple of paragraphs of detail, vector triple product. They use the word parallelepiped because that box doesn't have to have corners. You can have angles like this. So it's going to look like if you made a box and you could lean the sides, So the word for when every face is a parallelogram is parallelepiped. It's not meant to be intimidating, it's just a long name. All right, on to number 3, that one right there. So we do a vector plus 5 times a vector. They're both 3D vectors. So a vector plus a vector is a vector. No worries there. Problem 4, a 3D vector plus 5 times the length of a 3D vector, which is a scalar. Well, you can't add a scalar to a vector. So that's why that one gets nonsense. All right, let's see what else we got here. I got some more problems for you. There we go. Sorry, I skipped number 5, so there is no number 5 problem. Don't panic. We're just doing examples. So here is a 2460 crossed with a 1000. This is going to be nonsense because, look, you can't cross a 4-dimensional vector with a 4-dimensional vector. The cross product is built for 3-dimensional vectors only, and you can't cheat it and say, well, look, the 4th coordinate counts as 0. First of all, you can't just discount a coordinate. You can't. And if you are going to discount a coordinate, how do you know you can discount the 4th one? What if you just discounted the 1st one? How do you know which ones are discountable? Discount the 2nd one of each. But you don't do that. That just doesn't come up. So this has to be nonsense. Here's a 4-dimensional vector plus a 3-dimensional vector. Well, you do vector addition by coordinates. So that 8 has nothing to add to. Well, that's nonsense then. You can't add by coordinates and pretend the 8 is getting added to 0. You can't. You don't get to pretend like that. You add by coordinates, and if the coordinates don't match, then it's nonsense, period. Any situation, that's what's going on. Number 8, we have a 3-dimensional vector, but its length. So the magnitude of the 3-dimensional vector, and then there's no symbol here, so that's multiplication. A scalar times a vector is fine. A scalar times a vector is okay. It just takes this number, the length of that vector, times the vector itself. Perfectly legal, so that would be a vector. I got one more thing for you, and it's this problem. Let's take it nice and slow. You should have a homework section of a bunch of these things. So we're going to have a line L, and it goes through 2 points, actually. What happened here? We lost a point. Let me fix you up. And, whoops, there's another point. And the point, it's going to be in black. Just deal with it. -1, 0, 1. Okay. So the line L goes through 1, 0, -1, and -1, 0, 1. And the first thing to think about is, okay, L is going to be perpendicular to the plane. So that's like this. You've got the plane and you got L perpendicular to it. Easy. Oh, that's the normal. Now, I don't need the whole equation of the plane, do I? Because the normal is the direction vector in this case. So it saves me a lot of work. So don't go and get the full equation of the line, especially since it wasn't asked for. So don't go and get it. And then just get the direction vector. So that's head minus tail. That's right here. Head minus tail. That's subtraction. Let's see if I can get the whole picture here. That looks better. So you got the head minus tail, and that gives me the normal vector. And you can use 2, 0, -2. You can use that as your normal vector. It's okay. You won't be wrong. And you might get something at the end where you can divide your whole answer by 2. And if you don't divide it by 2, it's not like I'll mark you wrong. But anyway, if you use the simpler, since there's a common factor in your direction vector and you're going to use it for the normal, you may as well strip it down. 1, 0, -1. In this case, we're going to use as the normal. Now, if you did the subtraction in the opposite order, you'd have -2, 0, 2, which means you could use -2, 0, 2 or -1, 0, 1. Won't make any difference. You're going to get something that's logically equivalent to the answer that I have. So I would notice. If your answer is different from mine by a multiplication of 2 or by a multiplication of -2 or a multiplication of -1, I will notice and not mark you wrong. So anyway, so this is the generic equation of the plane right there. I've got numbers for the big A and the big C. The big B is a 0. So I get x minus z equals d, and we have a point that has to be in the plane. So this has to satisfy the equation of the plane. So just substituting in for x and z, I find out what d is. So d turns out to be 2. The plane has this equation. Now that answer makes a lot of sense to me, because if you look at this line, it has 0 for all the y coordinates, which means this line lies in the xz plane. That line lies in the xz plane. And now we're saying here that the plane has only the letters x and z in the equation. It doesn't have the letter y, which means the plane is parallel to the y-axis, which if you're thinking about, you want to get a line perpendicular to this direction vector, perpendicular to that, It sounds like, yeah, it sounds like it should have no y coordinate. You might want to think about this, maybe build a few examples in 3D and look at what I'm talking about. Thinking in 3D, this answer makes sense. So maybe we'll do some more of that on Wednesday, thinking in 3D. You live in 3D, so get some coordinates and you can do this very problem in 3D and verify that the answer is correct, like you would do that. All right, well, there you go. Talk to you later. Bye-bye.